Good afternoon and welcome. My name is Dan Williams and I'm a member of the KubeCon Program Committee and your track host for this session. Just a reminder, if you could give your feedback for this talk after the talk via sked.com, that would be greatly appreciated. Sam and Max both work on containers at AWS, helping build core components behind AWS Fargate, Amazon EKS, and Amazon ECS. Sam has been a Docker and Moby contributor since 2015 and a Containerd contributor since 2017. Max is a Containerd maintainer, and both Max and Sam currently help build firecracker-containerd to run containers with hypervisor-provided isolation. So without further ado, Sam and Max with extending Containerd.
Cool. So thanks for that introduction. I guess I don't have to really introduce myself anymore, but we're really happy to be here today to talk about extending Containerd. So we can start with just a brief overview of what we're going to talk about today. First thing, I'm going to just a brief introduction of what Containerd is, talk a little bit about its architecture and the modularity of that architecture. We'll move on to some of the extension techniques, and then we'll have some examples. So first, we're going to talk about Containerd. I hope that if you're at this talk, you're at least somewhat familiar with containers, and maybe you've heard of Containerd, or maybe you've used it, or some of the people here work on Containerd, which is also really cool. So just for anyone who's not super familiar, it's a really small and focused container runtime. It has a really limited scope. So it's a container runtime that was built by many of the same folks who've worked on Docker with a lot of the lessons learned from things that worked really well in Docker and things that were a little bit more challenging in Docker. So it has a bit of a different focus. It's really just focused on running containers and not any of the higher level things that Docker does. Things like overlay networking or built-in logging features or clustered storage are all out of scope for Containerd. So it's really just focused on the core problem of running and managing containers. And it's built out of these modular composable pieces that can be extended, and that's the main thing that we really want to talk about today. So I can give you a little bit of an overview of what the architecture looks like. It's a bunch of independent pieces that are meant to work well together. The primary way that you interact with Containerd is through the gRPC API or an adapter like the thick client library that's provided by Containerd. Typically, the users of Containerd are not someone interacting on the command line, but are rather a higher level application like a container orchestrator that's meant to integrate with Containerd. So this diagram shows some of the components, and we're going to take a look at a couple of them. The first one that I want to highlight is Containerd's content store. This is used for storing the raw content of images. That's usually things like compressed image layers. When you pull an image with Containerd, it ends up in the content store. And the layers are typically stored in an archive format like a tar and are not extracted onto the file system. So I want to talk a little bit about just what are layers, because this is a little bit interesting and relevant. In container images, you usually have some sort of concept of a union file system that composes different layers together. I've got a diagram here that tries to show this a little bit. So you can see that there's 3 layers in the bottom. The one that's labeled the base layer is a read-only layer and has a few files in it. There's an intermediate layer above it that has one of the files that goes straight through it, another one that is modified or replaced, and a third one that's deleted. And then there's a top layer which has another new file and shows 2 of the files that are shown through from previous layers. The way that layered file systems work is that the files stay in the layer that they're originally written in. So something that was in that base layer doesn't have to be duplicated in the other ones. This lets you enable things like sharing layers between different images and lets you have a really fast, cheap startup time because you can put an empty writable layer on top without having to copy all of the content. So why am I talking about this? The content store that we talked about stores layers in a compressed format and doesn't actually implement this copy on write or the union of the file system. So that's implemented by the next part of the Containerd stack, which is the Snapshotters. Layers from the content store are unpacked into some sort of file system in the Snapshotter, and the Snapshotter is typically implementing copy on write functionality so that you don't have to duplicate all of the contents. If you've used Docker before, you've seen this in Docker's storage or graph drivers. The Snapshotters in Containerd are similar, but they have a little bit of different implementation choices. Just like Docker, there can be multiple different implementations of Snapshotters, and the different implementations can do whatever they want as long as they produce, at the end of the day, something that looks like a union of the file system together. And you have different implementations that can offer different trade-offs in things like speed or efficiency. Next thing that I want to look at is when you want to actually run containers, you use a runtime. Containerd will dispatch to some lower level runtime implementation that goes and implements the parts of containers that we're all familiar with. Things in Linux like C groups and namespaces, seccomp capabilities. In Containerd, by default, it uses the reference implementation of the OCI standard, which is called runc, and that does normal Linux containers through all of those Linux technologies. But you could plug in something different, and maybe something that wasn't even containers. You could have it run anything that fits either the OCI standard that Containerd supports, or Containerd also has a version 2, a slightly different way of interacting with runtimes. But it's built to let you run something different than runc if you want. The gRPC API is the central interaction point for Containerd. It mediates interaction with each of the parts of Containerd. So a client doesn't have to know about all of the different ways that Containerd is decomposed. It has a central place where it can interact and not have to call a bunch of different places. There's also a client library that builds functionality on top of the gRPC API that talks to multiple services. For example, the workflow for pulling an image actually involves a bunch of different API calls to different services as part of Containerd through the gRPC API. Things like actually storing the content in the content store, unpacking it into the snapshotters, and so forth. So what is Containerd's overall architecture? It's a modular core built of small separate services that are designed for extensibility. And to make it functional, you can use those services together. You have interactions that are modeled as interfaces through the gRPC API and plugin mechanisms that make it easy to replace different implementations when you want something different. And there's a client library that hides that complexity from you and ties it all together. So now that we know a little bit about how Containerd works, we can move on to some of the extension points where you can customize it. There's 5 basic extension points for Containerd. The first one is the thick client library that I talked about a little bit before. In Go, that models interactions as Go interfaces. And so it has the ability to let you swap some of the implementations of those interfaces for different things when you want to change the way that the client is working. The next is what I call CLI or executable plugins, which are programs that Containerd executes for you, and you can tell it to run a different program instead of the one that it's going to run by default. The third is gRPC proxy plugins, where you can implement the entire interface of one of the Containerd services in a separate program and have Containerd call into that program for you. The next one is dynamically linked Go plugins. These are dynamically linked libraries, shared object files that you can compile with Go and load into Containerd and have it do different things. And the last one, if you need something that is the most powerful, you can run built-in plugins where you've compiled your own build of Containerd and changed its functionality that way. So let's go a little bit into depth for these techniques. And the first one that we're going to talk about is the client library. So Containerd is built for programmatic interactions and models a lot of its functionality in this thick client library written in Go. The client library orchestrates calls across Containerd's gRPC API, but also implements portions of common workflows like pulling images. These common workflows are modeled with interfaces, and you can use your own implementation when you want behavior that is different from the standard behavior that Containerd has. Some of the downsides of this are that you do actually need to control the calling code for it. So if you're writing your own integration with Containerd, it's really easy to extend the client library and do something different. But if you're using an integration that someone else has already written, you're not going to be able to customize it that way. So let's dig into the pull workflow. In Containerd, the actual network transfer of images happens inside the client library, not in the Containerd daemon itself. This is really unlike Docker. So in Docker, there's a single API call for pull, and it handles all of the networking. In Containerd, it's decomposed into a bunch of different steps. And the client library handles orchestrating those steps for you. So there's a default implementation that can handle talking to a Docker registry, but it's really easy to customize if you need something that's different. For example, if you want to use Docker-style image names but reference a different network endpoint, or if you want to customize encryption settings or timeouts, it's really easy to do that from the client library. Or if you want something completely different, like a different transfer protocol, something like BitTorrent, you could do that as well. We ended up writing an implementation for Amazon ECR, the container registry that AWS offers, that uses the ECR API directly instead of the Docker API. And I'll show you a little bit about how we were able to do that. So this is the default interaction to pull an image using the client library. And this uses the default resolver, which is the thing that knows how to talk to the Docker registry. You can see here that it's fairly simple. It's just calling a pull function and passing the image and a couple of options that go along with it. To use a different resolver, like the one that we wrote for ECR, your call looks very similar. The only differences here are that you construct the resolver object that you want to use, and then you pass that resolver object to the pull function. And the pull function will know how to use the capabilities that the resolver provides. Some resolvers are going to require maybe a different image name format, and so you may have to change that as well. So what does it look like to go and build a resolver? This is the resolver interface, which is the basic thing that needs to be implemented. And it has 3 methods. So the first one is called resolve, and that returns 2 things that are useful and interesting. The first is a canonicalized identifier for the image, and that's in the Docker implementation, the thing that will turn a name of an image that includes a tag into something that is identified by a digest. It also returns a descriptor object that containerd uses in subsequent calls. There's 2 more functions here, and they look really similar to each other. There's a fetcher and a pusher, and these both return objects that know how to get content or how to push object to a remote. If you only really care about retrieving things, you can implement a resolver with just the fetcher. You don't have to implement the pusher, but if you want to both push and pull images, you need to implement all of these parts. So let's look a little bit at the fetcher interface. This has one method that takes a descriptor and returns a reader for a stream of data. And the client can call this and then have access to whatever it's trying to retrieve. So the descriptor is what specifies the actual object that's trying to be retrieved. And images consist of a bunch of different objects, things like an index and a manifest, some config, and all of the actual layer contents. And this fetch method will get called once for each of those objects that needs to be retrieved. Some of the calls are going to involve, for example, if you're calling fetch for the index, the next call you're going to use the data that you retrieved from the index to call and get the manifest, and then the next call is going to use the data that you retrieved from the manifest to go and actually get the layers. This means that the same fetch method is used for all of the different objects that make up an image. The reader that's returned actually hides the implementation of the network activity from the client. So it's the responsibility of the fetcher to do whatever it wants to do. In the ECR resolver that we wrote, we have a fetcher that can make multiple parallel requests for different content ranges in the same layer that gets us a lot faster downloads than the default. If you wanted your custom implementation to be able to push images, you also need to implement the pusher. And this looks a lot like the fetcher. The main difference here is that it returns a writer where you write content instead of a reader where you're reading content. And you don't always have to use the same writer or return the same writer object out of this. In the ECR implementation, for example, we return different writers for different kinds of content. So we have a separate writer for manifest as opposed to the layer contents. So at this point, I'm going to hand it over to Max, and he's going to tell you a little bit more.
Hey, everyone. So Sam talked about client-side extensibility. Let's discuss server-side. Containerd has notion of executable plugins and uses them in a lot of places to extend its functionality. Essentially, it's a separate binary invoked by containerd at some point that conforms to certain conventions. And depending on plugin type, conventions might be different. Let's see how it works. First example of such plugin is Runtime. Containerd delegates the control of containers to run external binaries and communicates with them through a gRPC channel. Runtime handles all implementation details, how to run your containers. In containerd, there is runcv2 runtime that is used by default, and it uses Linux kernel primitives to run containers like namespaces, cgroups, and others. But it can be literally anything. For instance, in firecracker-containerd project, we have built our custom runtime, and it manages Firecracker micro VM instances instead of managing Linux kernel primitives. And inside of these VMs, we run containers. So what do we need to do to build a runtime? First, containerd expects name of the binary to be prefixed with containerd shim. so it's easier for users to list running processes on the system. Second, a binary has to be at path in order to be located by containerd. And the last one, it should support a few command line arguments. When containerd runs new container, it invokes a binary with a start argument. This indicates that we are about to start new container. It is expected that your runtime start a service in background and returns its address in std out back to containerd. It's up to runtime whether it runs a new background service for each container or it just reuses existing instance. Similar to start, containerd will call a binary with delete argument, so runtime implementations have a chance to clean up resources. So every runtime must implement task service interface over the domain socket. This is how containerd controls container instances. Here's how task service interface looks like. There are a lot of going on here, but most of this corresponds to a process lifecycle. So for instance, creates a new process and a container. There you specify a rootfs for your container, how to handle std out, and a bunch of other options. Similarly, start actually starts a process, wait will wait for the one to finish, and so on. You don't have to write your runtime implementation from zero. Containerd has helper packages to hide lots of complexity from you, like handling command line arguments, signals, login, events, or running at a gRPC server. So instead, you can focus on the service implementation itself. This snippet demonstrates how runtime endpoint might look like. Here, shim.run is containerd helper that hides all setup complexity. And you're only required to provide the service implementation. So when you have your runtime, now you have to tell containerd to use it when running a new container instead of default one. This can be done either through containerd client that Sam mentioned, or using CTR with runtime argument, like in this example. Another extensibility point is proxy plugins. They are similar to runtime plugins. It's a separate process that implements one of proxy interfaces. The only difference is that now you're responsible for a process lifecycle. That means that containerd doesn't invoke binary for you and there are no start and delete arguments. Instead, you have to configure containerd in advance and tell what kind of proxy plugin are you going to run and how to communicate with it. On early development stages of firecracker-containerd, we were developing the device mapper Snapshotter as proxy plugin. And that simplified our lives and gave us lots of room for experiments. There are two types of proxy plugins supported today. It's Snapshotter and Content Store. This talk will focus on Snapshotters. So Snapshotters are a mechanism for providing file system to containers. They implement layer union that Sam mentioned previously. So different Snapshotters implement different strategies how to deal with layers. So for instance, there is an overlay snapshotter that which copies entire file on each write, and there is a btrfs that does more lightweight block level copies. There are also offerings of block device-based snapshotters like device mapper and LVM. Similar to Runtimes, containerd has helper packages that provide gRPC wrappers for you. You would only need to implement snapshotter interface itself. Let's have a brief look how it looks like. These are used to control file system layers to be used by container. There are two major functions that worth to highlight. So for instance, when containerd pull in an image, containerd calls prepare to create a new layer. Prepare returns mount structures that can be used to mount snapshot for capturing changes. After that, containerd will unpack layer data from content store into the snapshot. And then containerd calls commit to seal the snapshot so it cannot be changed anymore. But it can be used as a parent or available for reading using view call. Also, containerd calls this interface for each image layer to build a chain of these snapshots. When running a new container, containerd will invoke prepare one more time to create a read-write layer on top of this chain of snapshots. So when proxy plugin is ready for use, you need to register it in containerd's configuration file. Here's how typical proxy plugin configuration would look like. Here type defines what kind of interface your plugin implements, and address is local socket file location which containerd uses to communicate with your proxy plugin. Similar to runtime, you have to tell containerd to use your proxy plugin. You can do that through client or using a CTR snapshotter command line argument. Another extensibility point is Go plugins. In firecracker-containerd project, we have built a gRPC API extension for containerd that would allow clients to manage micro VM instances. And our original intention was to implement it as Go plugin. But it turns out that there are a lot of compatibility challenges with Go plugins today. So for instance, compiler version that is used to build containerd and your plugin should strictly match, including major, minor, and patch numbers. Dependencies outside standard libraries that are used by both containerd and your extension should also strictly match. So you would need to have a separate Go plugin version for each containerd version, for each platform, for each architecture. And preferably, you would need an integration test to make sure it actually works, because you won't get any errors at build time. So instead, we ended up with built-in approach for our extension. The majority of containerd modules are built-in plugins. There are around 30 embedded plugins in 1.3 release of containerd. This includes default implementation of runtime like runcv2, a bunch of snapshotters, and various components for orchestrating runtime, snapshotters, and running containers. Every component can be extended, replaced, or deleted. But the downside is that this cannot be changed at runtime, and you have to rebuild containerd binary. You don't have to fork containerd to build your built-in extension. Essentially, you build your own program, import existing pieces from containerd, add your extension, and that's how you compose needed functionality. So how to build your own containerd distribution? Essentially, you have to write your own main function and register needed plugins. Here's how main would look like. You define minimal entry point to spin up plugin engine and run several listeners of containerd. Next, within same main.go file, you register plugins by importing them as Go packages. Most likely, you would want to reuse existing functionality of containerd, so you import Go packages provided by containerd first. And this can be a pretty long list. And after that, you import yours one. In order to make it work like that, a plugin must register itself in init package function and provide all details about your plugin. Here's how typical registration code would look like. You must specify type of your plugin and identifier, so other plugins know how to refer to it. Optionally, you can specify a list of dependencies that needs to be available to your plugin. And at runtime, containerd will call initFN function to initialize your plugin code. And that's basically it. So let's do some demo to see how it works all together.
Is that everyone able to hear me? Yeah, okay. Hopefully everyone can see on the screen. So what I have here is a bare metal EC2 instance that's set up to run a bunch of stuff with the various integration points that we've written with containerd. So this is some programs that we've written that do all the stuff that we've talked about. So first thing that we're going to do, I'm just going to show you a little bit about what's installed here. So we've got a few things that are on there. I think it's a little hard to read, but there's, first thing that I want to draw your attention to is a thing called firecracker-containerd. This is our own custom build of containerd with a plugin that's built into it. So it was doing the process that Max was just talking about. The next thing that we can look at is there's a program here called Firecracker. This is actually the Firecracker virtual machine monitor that AWS uses to run virtual machines. We also have something in here called containerd shim AWS Firecracker. This is the runtime component that goes and interacts with the Firecracker process that's there. And then there's a thing in here called ECR pull that is able to, it uses a custom resolver to pull images from ECR. Let's see. So what we can do is we can go ahead and look at this Firecracker containerd thing. It is just running as a systemd unit right now. We can go ahead and look at the systemd unit file if you're curious about it. Just looks like a normal systemd unit. So let's go ahead and look at what images are present on this instance that I have set up. And we're just going to go ahead and list them, and there's nothing there. So we can go ahead and pull something first, and we're going to use that ECR pull program that we wrote that's going to pull the Amazon Linux image from ECR. And it can go ahead and pull that, and it unpacked it into the device mapper snapshotter that we're using. So we can go ahead and see that that pulled properly, and you can see that it's there. So even though we didn't use the CTR command line to pull the image, we were able to pull it through the containerd APIs and using the different resolver that we wrote. So let's see what it looks like to go ahead and run something. First thing is, can you hear me? Okay. First thing, we can look at what this instance is running right now. So this is what looks like it's a Debian kernel, and it's got a host name that looks like an EC2 instance. And we can go ahead and look at the OS release file, and this just is a normal Debian thing. So what we'll do is we'll go ahead and run a container, and we'll go look at the same stuff inside the container that we were looking at outside, and we'll see what looks different. And we're just going to call this container demo. That's what that's on there for. So we've got a container running, and we can do the same thing that we were doing before, and we can look at the kernel that's running, and you can see it's actually a different kernel. So this is an Amazon Linux 2 kernel that's running inside a virtual machine. And it's got a host name that was set to just a micro VM. We can look at the same OS release. And you can see that this is an Amazon Linux image. This is actually the same Amazon Linux image that you'd be able to run with Docker. And so this OS release file is the same file that you would see if you were running things with normal Linux containers. But you could see that we're actually running a different kernel, which will distinguish it from running just a regular Linux container. Okay, so that was, I think, a little bit interesting. But what we can also look at is what happens on the host when you're running something like this. So we can go ahead and run another container, and we're just going to let it sleep in the background for a little bit, and we can examine what is going on with the way that the processes are set up on the host. So we've got a container, and we're running it. And what we can look at is what's going on with the processes that are involved. So we'll look at the Firecracker containerd process, and we're just going to look at the processes that are run here. And you can actually see a little bit that's different here from a normal container is instead of you being able to see the container processes that are running, like you can't see anything here that's called sleep, you actually just see this Firecracker process, and that's the virtual machine monitor that's running, and all of the things that are happening inside the VM are encapsulated by that. And so that's pretty much the end of the demo that I have here. So just to go over what we saw, we were able to pull an image from ECR using a custom resolver that we wrote. Then we were launching that container inside a VM using the custom firecracker-containerd binary with this control plugin built in, and using the containerd shim AWS Firecracker to go ahead and control the containerd or to control the Firecracker process. We used the device mapper snapshotter that we wrote, and we were able to contribute upstream. And so that was running with the upstream installed version of the device mapper driver. And then inside the VM, it uses the normal containerd shim to go ahead and run a container with runc. So at this point, I think we're ready for questions.
What was that other Go plugin type again? The one that's not a snapshotter?
The other Go plugin type that's not a snapshotter?
Content store?
Are you talking about like being able to run a gRPC proxy plugin, or the just like a normal Go plugin. So gRPC proxy plugin. The other,
Content store and
so I think there's only two that are supported right now. There's the Snapshotters and the content store. The only one that we implemented as a proxy plugin was the Snapshotter.
Any other questions?
This is great. What are your productization plans or that you can disclose? What are you going to do with this stuff? Looks great. When can I use it?
So we've been building firecracker-containerd to hopefully help people run containers with a hypervisor boundary that gives you a little bit of a little bit of a stronger isolation between different things that are running on the same underlying host. So in the way that we think about this is it's aimed at things like multi-tenancy and at isolating workloads from each other that are operating in different security contexts. You can see, so Firecracker was something that was built for AWS Lambda, basically, and for use cases that are the same kinds of use cases for Fargate. So this is software that we're writing to help make that available for other people that want to run that as well. I think there's one in the back.
Does your containerd plugin work with Kubernetes? Like, you didn't show the part there. How does it integrate back to Kubernetes?
I can't hear very well, but you're asking if this integrates with Kubernetes, is that correct?
Yes. How does it work with Kubernetes? You didn't show that part.
So Firecracker-containerd does not work with Kubernetes today. The way that it will hopefully work eventually is through the CRI. So containerd has a built-in plugin called CRI containerd that implements things with Kubernetes. There's a few design challenges that we're still facing in order to get something working with Kubernetes today. But if you're not using Kubernetes and if you're integrating directly with containerd, you're able to use this today.
Can you tell us about the different production issues you have seen using the Firecracker so far?
You're asking about different production issues that we've seen using Firecracker? I'm not sure what you mean by that question.
Did you hit any red flags where you believe Firecracker is not ready?
So Firecracker itself is being used in production and is ready for production. The Firecracker containerd project is something that we're still working on. So that's the integration with containers part.
So what are the top issues you have faced so far?
I can't hear very well.
What are the top issues that you have faced so far?
The top issues that we've faced running Firecracker? I don't think that I'm qualified to comment on that right now.
What do you see as the main benefits to using containerd over Docker? I noticed you said that it was forked out of Docker, but what are like?
So for me, the things that I really like about containerd are the fact that it is a bunch of separate things that are composable and interchangeable. And so I can work out different things and build different things than were initially envisioned by the people that wrote containerd. And so it let us build this whole thing with Firecracker. It let us build the thing where we're able to pull things from ECR. Versus something like Docker is a little bit more of a monolith. It hides a lot of functionality behind a fairly high-level API. And so if you want to do things that are not standard with Docker, it's a little bit harder.
I think we got time for one more question.
Where can I find all the Firecracker containerd stuff so I can play with it?
So all the Firecracker containerd stuff is on GitHub. If you go to github.com/firecracker-microvm, all of the Firecracker code is under there. So the main Firecracker project is there, as well as Firecracker containerd. Yeah, everything that was shown on the demo is open source, and that's all on GitHub. The ECR thing is under the AWS Labs GitHub instead of the Firecracker one because it's not really related to Firecracker. But everything that we showed today was open source. So I think we're out of time at this point. One last thing before we finish, I would really appreciate it if you all would fill out the survey that's on the Sked website or the Sked app. We really appreciate feedback. Hopefully they're going to actually send it to us. Something to keep in mind is that as you're filling these out, that everyone who's presenting here is a human just like you, so hopefully don't be like too mean to everyone. If you didn't get a chance to ask a question here, the hallway track's open. We're going to be around the whole week. You can come up to us at the end of this session. If you find us in the hallway, feel free to come say hi. If you didn't get a chance to actually talk to us in person, our email address and Twitter handles are up there. And so thank you.